Hello, everyone. We're going to go ahead and do section 6.2, which is on ratio, proportion, and variation. As an overview, we say the most obvious way to compare two numbers is to subtract them, but is there a better way? The answer is yes. Division can provide better comparisons for us to use. If you're comparing the price of a Coke at two different stores and the prices are $1 and $2, that dollar difference is significant. It's what we call double the price. If you're comparing two TVs at the price of $1,200 and $1,201, they're essentially the same price. They're only different by a dollar, but we could divide that, and that would give us the division there of 1.0008, meaning that it's only different by that 0.008 kind of margin, which is super small. So those are essentially the same, only different by a dollar. Just like how the Coke was also different by a dollar, but by that difference of a dollar, it made it double, while the difference of a dollar between the two TVs was like almost negligent at that point. So we can compare two numbers by dividing them, and that creates what we call a ratio. So we can get a ratio by dividing two quantities by each other. So ratios, we say that a ratio is a comparison of two quantities using division. For two non-zero numbers A and B, the ratio of A to B is written as A with a colon B, and it's read as A to B, so A to B, or A divided by B, A over B. So, as an example, in 2021, about 52% of all smartphones in the US were iPhones and 48% were other models. We'd say that ratio was 52 to 48, or 52 with a colon 48. So we can write that as that ratio. You could also say 52 divided by 48 or 52 over 48. Those are other ways to write them. We have this little alien sitting here. He's holding up the ratio 3 to 4. And he's thinking of all the different ways that that ratio could actually be written. You could write 3 over 4. 3 divided by 4 is 0.75, so that's the decimal value of your ratio. The percentage value would be 75% of that ratio. So there's many different ways of expressing ratios, fractions, decimals, percentages, things like that. So ratios are most often written as fractions in math, so we can do arithmetic with our ratios. Since ratios can be expressed as fractions, we can reduce ratios the same way we reduce fractions. So having 10 divided by 15, 10 and 15 are both divisible by 5. So we can reduce them both by 5. 10 is 5 times 2, and 15 is 5 times 3. So if you divide out the 5 in each of those, you would get 2 over 3. So 10 over 15 is the same as 2 over 3. So the ratio 10 to 15 is the same as the ratio 2 to 3. So you can reduce ratios the same way as you reduce fractions. So we're going to do a quick example. We're going to suppose that we compare the lengths of a 2-foot board and an 18-inch board. First, we'll explain why the following ratio is actually misleading, and then we'll give an accurate comparison. So the ratio that's been provided to us is 2 over 18, but this is misleading because we were given 2-foot board and 18-inch board. They are in different units. So because they're in different units, this ratio that we're given is very misleading because it's 2 feet over 18 inches. So whenever we do ratios, we want them to be in the same unit. So that's what we have here. The ratio above is misleading because it looks like the 18-inch board is a lot longer, but inches are much smaller than feet. So 2 feet is actually going to be the bigger unit, but it doesn't look that way in our ratio. So to accurately compare, we need them in the same units, so we can convert 2 feet into 24 inches. Converting feet into inches is a little bit easier in this situation than converting inches to feet. 18 inches to feet would give us a decimal, and we'd just rather not, right? So we're going to turn 2 feet into 24 inches. That would make our ratio 24 over 18, which can be reduced down to 4 over 3. So 24 and 18, they're both can be reduced by 6. 24 times 6 times 4 is 24, and 6 times 3 is 18. So you reduce by 6 to get 4 over 3. So that is the actual accurate comparison of our two boards there. It's in a ratio of 4 to 3. So our 2-foot board and our 18-inch board, that ratio is 4 to 3. There we go. So that leads us into proportions. So when two ratios are equal, they can be written as what's called a proportion. So you have your two ratios set up in fractional form, and then you set them equal to each other. A proportion is an equation in which two ratios are stated to be equal. So something like A over B equals C over D. Those two fractions, A over B and C over D, are equal if A times D equals B times C. We could do this by cross multiplying. So you may have done this before, but if not, here's a little mini lesson. We say this is called cross multiplying. So if you have your ratio A over B, and that's equal to C over D, cross multiplying means you're going to multiply the numbers that are across from each other, and you're going to keep the equal sign. So we would multiply A and D. So the numerator, that's the one on top, times the denominator, the one on the bottom of the other one. So numerator of one times denominator of the other. Denominator of one times numerator of the other. So A times D is equal to C times B. And that's our equal part there. So that's called cross multiply. We have another example here. We have 5 over 6 and 15 over 18. So we multiply 5 times 18 by 6 times 15. Now these are real numbers, so this is establishing that two ratios are equal. So 5 times 18 is equal to 6 times 15. And those are both equal to 90, which means that these ratios here, 5 over 6 and 15 over 18, are both equal. So we can use cross multiplying to solve any proportions or ratios, or you can do it to check to see if two ratios are equal to each other. So we're going to use our example here to decide if each proportion is true or false. So starting with A, we have 5 over 2 is equal to 25 over 4. So we're going to cross multiply, which means that we're going to multiply 5 times 4 and set that equal to 2 times 25. So we have 5 times 4 is equal to 2 times 25. We want to simplify this. 5 times 4, you can use a calculator or your brain, is going to be 20, and 2 times 25 is actually 50. That is not equal. That means that that proportion is false. So if they're not equal, that means your proportion is false. Those ratios are not equal to each other. So there we go. Now we'll go on to B. We have 11 over 3 is equal to 55 over 15. So we'll cross multiply 11 times 15 and 3 times 55. So we have those there. Now, brains or calculators are going to multiply 11 by 15 and 3 times 55, which gives us 165 for both. So we get 165 is equal to 165, which means that our proportion is true. Ooh, too far. That means our proportion is true. So if they're equal to each other, that means your proportion is true. Your ratios are equal. But if they're not, then they are not. All right. Now we're going to go ahead and do an example together. So while on a spring break trip, a group of friends burn 12 gallons of gas in the first 228 miles, then they stop to refuel. If they have 380 miles yet to drive and the SUV has a 21-gallon tank, can they make it without refueling again? So we have a kind of ratio set up here. They were able to drive 228 miles on the 12 gallons of gas. So we can establish that ratio 228 to 12 or 228 over 12. And then we want to know if the SUV has a 21-gallon tank and we refill, will we hit 380 miles? Can we make it? So it would be tempting to do 380 over 21. But that 380 is actually kind of just like a flag marker for us. We don't know how many miles we'll actually get out of that 21-gallon tank, but we're hoping it will be at least 380 so that we don't have to stop again. So that's kind of what we're trying to establish here. So we're going to keep that thought. We're going to go on ahead over to our notes. All right, so let's highlight our important information. We said that we burned 12 gallons of gas in the first 228 miles. Then we want to know basically how many miles can we go on a 21-gallon tank with 380 miles left to drive. So we're highlighting this. Let's actually do a different color. We're going to highlight this in a different color, 380 miles, because remember, that's not necessarily part of our problem. It's that flag. That's what we're trying to reach. That's the goal. So we want to make that just a little bit different, and we can write that here. We'll put a little arrow there. This is the goal, not necessarily part of the problem. So our problem is to set up proportions. Now we know that it took us 12 gallons of gas to go 228 miles. You can write them as 12 over 228 or 228 over 12. Whichever way that you do it, you just want to make sure that the other one follows the same gallons over miles or miles over gallon, but it doesn't matter which way you write it, just as long as the same units are across from each other. So like miles need to be on the top and gallons need to be on the bottom, or gallons need to be on the top and miles need to be on the bottom. You just want to keep it one way or another, but the order doesn't necessarily matter. Personally, I like to have bigger numbers on the top and smaller numbers on the bottom, so I'm going to put the miles on top and gallons on the bottom. But like we said, you can flip that if you want. So we're going to put 228, and this is in miles, over 12 gallons, and this is equal to some number of miles because we don't really know. We don't really know that number of miles. So we're going to fill in the gallons because we know there's 21 gallons in the tank and some questionable number of miles. Now we don't know the number of miles, so it can feel natural for us to write like a question mark. But in math, instead of question marks, we write variables like X. So, we don't know how many miles 21 gallons on our tank could get us, so we're going to write an X. If you want to keep it as a question mark, you certainly can. But we're going to write X instead of the question mark. So we're just going to make sure that at the end, that X hopefully reaches at least 380, because that means that we wouldn't have to refuel again. But if it doesn't reach 380, that just means that we would have to refuel again at some point. Okay, so we have our proportions set up. Now we're going to cross multiply. So when we cross multiply, like we said, we go across, like I established earlier. So we do 228 miles by 21 gallons. And then we would do 12 gallons by X miles. So we multiply across. So we would get 228 miles times 21 gallons. And then we have 12 gallons by X miles. Now, at this point, we can drop the units. We don't need to write miles and gallons anymore because we made sure that they were the same units across the top and across the bottom. So you don't have to write them anymore. You could if you wanted to. You would just have miles and gallons, miles and gallons. It's technically miles per gallon in this case. So we have 228 times 21 is equal to 12x. So we're trying to solve for x because we want to know how many miles that 21-gallon tank is going to get us. So we can use our calculators or our brains to do 228 times 21. So if you use a calculator or your brain, you're going to get 4,788 is equal to 12x. Now, we want to solve for x, and so we want to get rid of that 12, and the 12 is being multiplied, so we're going to divide both sides by 12. And so calculators or brains, we go and do 4,788 divided by 12, and that will give us 399. And x, like we said in the beginning, this was miles, so X would be 399 miles. So our question, could they make it without refueling again? They just needed to make that 380-mile mark, that flag there, and yes, we can. It's 399 miles. That means that we would arrive at our destination with 19 miles left over on the gallon there. So can they make it without refueling again? Yes, they can make it without refueling again. And there we go. So the answer is yes, we made it. So there we go. So that's a word problem using proportions. We can kind of see how the word problem is used in order to calculate a proportional type of problem. So, all right, let's go ahead and go on over back to our lecture. All right, so now we have variation. So two quantities are often related in such a way that if one goes up, the other does as well. And if one goes down, the other will go down too. This is called a direct variation. So if two related quantities, or if two quantities are related and one goes up, the other will go up. And if one goes down, the other goes down. So that's your direct variation. Now, a quantity y is said to vary directly with x if there is some non-zero constant k such that y equals k times x. The constant k is called the constant of proportionality. So if you have some direct variation, then you'll probably have some sort of constant of proportionality in there, k. That makes the values of x and y different, but we still see them going up at the same, time and down at the same time. Sometimes quantities are connected so that when one goes down, the other goes up. And that is called inverse variation. So in those types of cases there, we have kind of a seesaw type of problem there. So we say a quantity y is said to vary inversely with x if there is some non-zero constant k such that y equals k over x. So we have that seesaw relationship going on. So when one goes up, the other one goes down, and we have that as varying inversely. And so your constant proportionality is being divided by that value of x. So we see the different variation types and kind of what that means with their equations. So direct variation has y equals k times x, but inverse variation has y equals k divided by x. So we're going to go ahead and do an example, a quick example together. So we suppose that you earn $95 per day. We're going to write a variation equation that describes total pay in terms of days worked, and then use it to find your total pay if you work 6 days, and if you work 15 days, we'll say if. So we're going to have a variation equation here for this. So we're going to let y equal the total amount that you earn. Then we're going to let x equal the number of days that you work. And our constant of proportionality is 95. Now, at this point, we didn't actually explicitly say if this was direct or inverse. So we kind of want to look at our problem again. We suppose $95 per day. So if we have a number of days that we already know, we would earn 95 for every one of those days. That ends up being multiplication. So 95 times 3 for working 3 days. So in that case, that means that this is a direct variation. Even though it didn't explicitly set it, it's kind of embedded a little bit in the problem. So we have y is the total amount that you earn, x is the number of days that you work, and k is $95 per day. So our variation equation, our direct variation equation in this case, would be y equals 95 times x. 95 is your constant of proportionality there, and x is the number of days that you work. So if we want to use it to find the total pay, if you work 6 days, that means that we'll replace x with 6. So for x equaling 6, we'll do y equals 95 times 6, which comes out to $570. So if you work 6 days, you earn $570. Then we can do the same thing for 15. So if you work 15 days, we would get y equals 95 times 15, which equals 1,425. There we go. So that's a direct variation equation there. We just have 95 times the number of days, so we can find out how much we would make by working any number of days. So let's do another example. We say in construction, the strength of a support beam varies inversely with the cube of its length. So it is inverse, so we're using the inverse variation, but then also we're told the cube of its length. If you don't quite know what that means, cube means to the power of 3. So the power of 2 means squared. Square is a 2D object, but cube is the 3D version of it. 3 dimensions, 3 units, so 3 power. So that means it's the length to the power of 3. So that one's an important part to notice there. If a 12-foot beam can support 1,800 pounds, how many pounds can a 15-foot beam support? So we were told that the strength of the support beam varies inversely. That means the shorter it is, the more it will support. So the lesser that foot value is, the lesser the length, the higher the support. The higher the length, the lesser the support. So we're going to see that inverse relationship here. We're extending the length. We're saying it was 12 foot, now we're doing 15 feet. That means that the support will be going down. So the 12-foot beam could support 1,800 pounds. The 15-foot beam is probably going to support less because it's inverse. So, all right, let's go ahead and do this one together in our notes. All right, so like we said, this problem is an inverse variation. So we want to write that, just remind ourselves, inverse variation is y is equal to k over x, some constant of proportionality divided by x. So that's our inverse variation equation there. We want to define what x and y are, just so we're very clear. Y, in this case, is the strength of the support beam. So it's the strength of support. So strength of support beam. X is the length of the support beam. Now, and then what we also discussed was that the cube of the length, that's going to be the length, the power of 3. So cube of length is length cubed. We said that x is the length. So really we're talking x cubed. So our inverse variation in general is y is equal to k over x. But in this case, our problem is telling us that it should be k over x cubed. So we have the inverse variation, kind of the general one, but now we're going to write inverse variation for our problem. So it's a little bit different. Y equals k over x cubed. Wrong color. It's kind of hard to see. Let's turn that down a little. There we go. So that's our inverse variation for our problem, k over x cubed. So we use that inverse variation, the generic kind of problem there, and then we changed it from what our problem stated. So we have our inverse variation equation for our problem. All right, so now we need to figure out what our inverse variation is going to be for the 15-foot support beam. Now, we could definitely figure that out if we had K, but we don't have K. So what we'll need to do is we'll need to take the information from our problem in order to solve for K. So we're going to put a little star here. We don't have K. Let's go with we don't know K. That's probably a little bit better. We don't know K. So we need to use our problem information to find it. So, like we said, we don't know K, but we do know that a 12-foot beam supports 1,800 pounds. So we're going to use those facts in order to help us find K. So we're going to use those facts. We know that Y is equal to 1,800 when X is equal to 12 from our problem, 1,800 pounds, 12 feet. So we can go ahead and create our equation here. Y, it's not Y, it's 1,800. There we go. 1,800 is equal to K over 12 to the power of 3. This is going to help us find K. So we're going to go ahead. We're going to start solving this. So the first thing we want to do is figure out what 12 cubed is. So we've got 1,800 is equal to K divided by, that's going to be 1728. So 1728. There we go. So we want to solve for K in this case. K is being divided. So what we want to do is multiply by what K is being divided on both sides. So we're going to go ahead and we're going to multiply each side by 1728. And this becomes 1,728 times 1,800. And this is going to be equal to K. So we're going to go ahead, we're going to use our calculator to calculate 1,728 times 1,800. So we end up getting that K is equal to 3,110,400. So by using the information that we did have, that we were given with the 12-foot beam supporting 1,800 pounds, we use that in order to find K. Because now that we have K, we can go ahead and we can figure out the inverse variation, the inverse relationship for the 15-foot beam. So now that we have K, we're going to go ahead and do the same or similar thing. For the 15-foot beam, we're going to have Y is equal to K, 3,110,400 divided by X cubed, where X is 15. 15 cubed. So we're going to go ahead, we're going to solve our relationship here. So we can go ahead and figure out what 15 cubed is first. So this will be 3,110,400 divided by 15 cubed, which is 3,375. So then we're going to go ahead, we're going to put this in our calculator, and we're going to find our answer. We're going to round if necessary. If we don't have to round, then we won't. But if we do need to, then we want to do that. So when we put this in our calculators, we do get a decimal answer, but we don't need to round it because it just has one decimal place. This will be 921.6. And it just ends there. So there's no need to round anything. We're just going to keep it as 0.6 to keep our answer exact. And this was the strength. So this is how many pounds your 15-foot beam can support. So we can write our answer as a word, a word answer here, but this is our numerical answer, 921.6. But we could say the 15-foot beam can support 921.6 pounds. And there we have it. So like we said, this was an inverse variation. So that meant that the longer the beam became, the less weight it could support. So our 12-foot beam could support 1,800 pounds of weight, but just by adding 3 feet, we actually saw that that decreased by half or almost half. So by increasing 3 feet, we lost almost 900 pounds of support. So making beams longer in construction actually means that it doesn't support as much weight, which is not good. So we have that inverse variation there, that inverse relationship. The longer the beam gets, the less it can support. But the shorter the beam gets, the more it could support. So we can imagine, maybe how much more a 10-foot beam could support versus a 12-foot beam. So, all right, we went ahead and finished that example there. So let's go ahead on over back to our lecture. All right, and that finished up our section 6.2. So in summary, in section 6.2, we learned how to write ratios into fraction form, solving problems with proportion, and solving problems using direct or inverse variation. So all right, that wraps up section 6.2, and I'll see you in the next one.